In the next part of the tutorial, we will look into commonly used assays for assessing and optimization of PROTACs. We will discuss the importance of the formation of the ternary complex and explain the term cooperativity. A workflow from industry will be shown for PROTAC optimization. Two values DC50 and DMax are important to describe the cellular efficacy of a PROTAC. DC50 is a concentration of a PROTAC needed to achieve degradation of 50% of the protein of interest in a cell line compared to an untreated control. It is good practice to carry out measurements also for a control protein, for example actin or tubulin, to rule out unwanted effects on cell viability or cellular protein synthesis. The max is a maximum achievable reduction in protein of interest levels within a given time frame, usually measured between 2 to 8 hours. Depending on the protein of interest and cell line, resynthesis of the protein of interest will counterbalance later on the effect of a PROTAC. Thus, the resynthesis rate of a protein of interest is an important decision factor when starting a PROTAC approach. As a good practice, a certain time point should be selected to compare different PROTACs, clearly depending on the protein of interest, cell line and assay conditions. Various assay formats are used for the determination of DC50 and DMax, as well as the selectivity of a PROTAC. A typical concentration course carried out as Western blots shows that the DC50 of this PROTAC is around 2 nanomolar. However, at high PROTAC concentrations, only minor degradation of protein of interest is observed. This is a so-called hook effect. Let's explain this hook effect along the schematic graphs on this slide. Formation and stability of the ternary complex defines the degradation of the protein of interest. The degradation concentration curve on the right is reflecting an inverse bell-shaped curve for the level of ternary complex versus PROTAC concentration. With increasing doses of PROTAC, the ternary complex gets more and more prevalent. An increase of degradation of the protein of interest is observed till a maximum plateau is reached. Further increase of the PROTAC concentration does not increase the level of ternary complexes anymore, but more and more binary complexes are formed, and thus the degradation of the protein of interest declines. Finally, at high PROTAC concentrations, formation of binary complexes outcompetes completely ternary complex formation. One has to take this into account when studying PROTACs in vitro. Thus, it is a good practice to probe a wide range of PROTAC concentrations, at least 8 to 10 concentrations using half-log dilutions, to obtain a full DC50 curve of key PROTACs. Observing the hook effect is a good mechanistic indication of a ternary complex mediated effect, but it's unlikely that the hook effect has any strong relevance in the in vivo situation, because it is difficult to achieve such high concentrations with therapeutic doses. This slide gives an overview of assays used for PROTAC assessment and optimization. The color code for the assays indicates how the analysis is done. Red after lysis of cells, green in living, often engineered cell lines, blue when isolated purified proteins are used in these assays. In most cellular degradation assays, such as Western blots, the cell has to be lysed after PROTAC administration to measure protein of interest degradation and to calculate DC50 and DMax. By using engineered cell lines supplied commercially by specialized companies, it is possible to do this in living cells. An assay format such as nanobread allows, besides DC50 and DMax assessment, to determine binding kinetics, to observe ternary complex formation, or to measure PROTAC engagement in regard to protein of interest or E3 ligase. Also, cellular thermal shift assay (CETSA) can evaluate target engagement of a PROTAC with a protein of interest. In PROTAC optimization, it is convenient to use isolated purified proteins, the protein of interest, or the E3 ligase, or subunits such as the substrate receptor of a choline ring ligase. Depending on the assay format, this is done in solution, or proteins are attached on a chip or bead. Biochemical fluorescence assays help in determining affinities in a binary setting, for example between PROTAC and protein of interest, or for ternary complex formation. Biophysical assays such as surface plasmon resonance, isothermal titration calorimetry, or microscale thermophoresis offer the possibility to evaluate thermodynamic and kinetic parameters. Qualitative and quantitative analysis of the cell proteome by applying different methods of LC-MS allow the assessment of PROTAC selectivity as seen on the next slide. For more details about the requirements, advantages and drawbacks of these assays, please look at the one-page descriptions in the appendix of this PROTAC slide set on the EFMC website, Best Practices in Medicinal Chemistry. Comparison of the protein content of a cell treated with a PROTAC and an untreated cell, lysed after the same time and conditions and analyzed by modern LC-MS methods, gives an estimate of the selectivity of a PROTAC for the protein of interest. A volcano plot enables the visualization of this large volume of replicate datasets. Often more than 4,000 proteins are covered. The plot shows the magnitude of change in protein levels in a logarithmic scale on the x-axis, whereas the y-axis reflects the statistical significance of these changes, for example a p-value. Besides the degradation of the protein of interest, one can get further information. For example, if safety-related off-targets are affected by imide-based PROTACs, especially at higher concentrations. Time-course experiments allow to distinguish pathway effects from direct degradation of the protein of interest. For more details, please see Appendix 1. One should pay attention to the following points in performing such global proteomic studies. The applied PROTAC concentration should be around tenfold above the DC50 of the protein of interest, but below the onset of the hook effect. Sufficient incubation time should be chosen to reach the DMax of the protein of interest. At early time points, one might overestimate the PROTAC selectivity. Twofold or larger changes in protein levels should be reported, if the p-value is above 0.05. Several cell lines should be used in the proteomic studies to maximize proteomic coverage. In the shown example, a cereblon-based PROTAC degrader GB300 for the kinase Aurora A shows a DC50 of 30 nanomolar and a DMax of 78% in a hybrid cell assay after 6 hours. Its exquisite selectivity is reflected in the volcano plot, where only the protein level of Aurora A is significantly lowered after 6 hours exposure at the shown concentration of GB300 in a leukemia cell line. Let's come back to the term cooperativity. In the optimization of PROTACs, the dissociation constants of binary and ternary complex formation can be measured in some before mentioned assays using the corresponding proteins, the protein of interest and the E3 ligase or its subunit, such as substrate receptor, cereblon or VHL. The quotient from these two dissociation constants is a so-called cooperativity ratio alpha. In the case of non-cooperativity, alpha equals 1, there is no additional influence on the ternary complex formation by these two proteins. If alpha is noticeably above 1, additional positive, for example stabilizing protein-protein interactions between protein of interest and E3 ligase or subunit, are occurring due to the induced proximity by the PROTAC. Positive cooperativity describes the enthalpy contributions from these interactions. It leads to the increase in the amount of the ternary complex formed and widening of the bell-shaped curve, thus leading to the decrease in time needed for the degradation of the protein of interest. There are distinct benefits from positive cooperativity observed for a PROTAC. Increased stability or prolonged half-life of a productive ternary complex leads to sustained and fast protein of interest degradation. On the other hand, a weak binary affinity of a PROTAC to the protein of interest can be compensated by positive cooperativity. As mentioned before, positive cooperativity might be a major factor in the surprising selectivity of a PROTAC, for example when starting from a promiscuous ligand. But there are also some caveats in regard to cooperativity. There is not always a direct correlation of cooperativity with degradation. Sometimes even negative cooperativity can still lead to detectable degradation, however at a very slow rate. Even when a stable ternary complex is formed by a PROTAC, no degradation of the protein of interest can be observed in some cases. An unproductive ternary complex is formed. Reason might be a slow, insufficient ubiquitin transfer from the E2 enzyme to the protein of interest, or lacking of a reachable lysine on the surface of the protein of interest. This reflects the kinetic characteristics of the cellular degradation of a protein of interest by a PROTAC hijacking the UPS. One can summarize the current best practices in regard to cooperativity and ternary complex formation. PROTACs should be optimized based on a suitable degradation assays, looking at the rate and extent of the protein of interest degradation. Ubiquitination of a protein of interest measured in specific assays correlate directly with the degradation rate, due to the formation of a productive ternary complex by the PROTAC. Assessing cooperativity can help rationalize findings such as surprising selectivity and support further design of optimized PROTACs. An illustrative example for positive cooperativity is shown here. In PROTAC MZ1, a short glycolinker connects a ligand to VHL and GQ1-like ligand to the epigenetic reader BDR4 involved in transcriptional regulation. The protein BDR4 possesses two bromodomains named BD1 and BD2, which are important for recognizing acetylated lysines during epigenetic processes. MZ1 shows high positive cooperativity for binding to the BD2 of BDR4. Alpha has a value of 17.4 and is higher than that for the other bromodomain BD1 of BDR4, as well as for the bromodomains of other close family members such as BDR2 and BDR3. Analyzing the X-ray structure of the ternary complex, one can observe additional positive interactions of the proteins. On the right side of this cartoon, a salt bridge is formed between the side chain of a glutamate of BDR4 and an arginine of VHL. On the left-hand side, a salt bridge of an arginine side chain with two acidic side chains of BDR4, glutamate and aspartate can be seen. Furthermore, a hydrogen bond is observed between a backbone NH and the side chain of the same glutamate. Taking all together, the van der Waals contacts, H-bonds and electrostatic interactions have led to this observed high positive cooperativity of MZ1 and the preferred degradation of BDR4 over close family members BDR2 and BDR3 in a cell assay. VHL and BDR4 somehow sandwich MZ1 and bury otherwise solvent-exposed regions of the involved proteins. The total buried surface area is well above 2,500 square angstrom. Many structures of binary complexes of ligands to E3 ligases or subunits have been reported. However, the number of published crystal structures of ternary complexes is still relatively small. Recently, the first cryo-EM structure of a ternary complex has been reported. The majority of these structures involves the substrate receptor VHL. In an overlay of several VHL-based ternary complexes, one observes differences in orientation of the proteins of interest in respect to VHL, whereas the backbone trace for VHL is nearly identical. Besides the rationalization of positive cooperativity, these structures supported rational drug design to improve PROTACs, especially in linker optimization in regard to length, rigidity, attachment points, and polarity. One should take in account that additional solution conformations of a ternary complex might contribute to protein of interest degradation besides the one obtained from crystallization. To gain further insight into the dynamics of ternary complexes, orthogonal solution-based techniques have been used, proton-deuterium exchange-based MS, or NMR-based techniques, especially in combination with or as basis for computational studies. Before engaging in elaborate optimization, it is best practice to verify that a found active PROTAC is really acting via the intracellular UPS. 4 validation methods can be applied. A negative control can be easily obtained in the case of cereblon or VHL-based PROTAC by slight chemical modification of the active PROTAC. For cereblon and methylation of the imported imide part will lead to a negative control. For VHL, a switch at the stereogenic center C4 in the hydroxyproline part will result in an inactive stereoisomer, an epimer with S configuration. Further methods are based on competition to the PROTAC by use of an excess of a protein of interest binder or of a ligand of the E3 ligase to which the PROTAC binds. Finally, using compounds interfering with the UPS should stop the protein of interest degradation by UPS hijacking PROTACs. MG132 is a proteasome inhibitor, whereas MNL7243 is an E1 inhibitor. Both would stop the action of a PROTAC. Furthermore, a NET8 inhibitor such as pevonedistat would prevent the necessary previous activation of Coulin ring ligases. One should check regularly the cell viability in the development of PROTACs by measuring the level of control proteins to rule out cytotoxicity or interference with protein synthesis, which could lead to false positive results. A typical workflow for the identification and development of a PROTAC for disease-related protein of interest has been provided by colleagues from Merck, Darmstadt, Germany. In the center you can see the main workflow where compounds are profiled. In silico, property predictions can help to synthesize appropriate PROTACs. Compounds are then screened at different concentrations and time points in cellular degradation assays, ideally with high bit or nanobread. Activity is then assessed in relevant functional cellular assays to check for adequate signaling of phenotypic effects. Measurements of polar surface area and lipophilicity during optimization can ensure that one stays within a range of physicochemical parameters to achieve the necessary cell permeability. Solubility measurements are also an integral part of the workflow, especially for the development of oral available PROTACs, and in vitro clearance is checked. While still useful to monitor, in vitro permeability assays for PROTACs are controversial due to their limited predictivity, and it's recommended to go in vivo rapidly to assess pharmacokinetics. Advanced molecules will then be tested for PK/PD, usually monitoring in vivo degradation of the protein of interest and efficacy in relevant disease models. As shown on the right, characterization and optimization of these compounds might be done in parallel using binding assays with isolated proteins. This can be used to determine binary affinities towards E3 ligase and protein of interest, or even ternary complex formation as well as selectivity. On the left side, additional assays to characterize selected compounds are shown. Mode of degradation should be demonstrated by early analogues. During optimization, evaluating degradation selectivity by proteomics is essential as previously mentioned. The influence of ternary complex formation on selectivity has been discussed before. For selected compounds, assessing cooperativity and, importantly, getting structural information via X-ray or cryo-EM can bring essential insights for the optimization.